Hi everyone, in this video I'd like to introduce the approach we used in the computation multi-data side time series anomaly detection. It's an approach based on neural network and data augmentation. I will introduce our method in 4 parts: basic idea, data augmentations, other details, and results. Since in the data side of this computation, different time series have different lengths, we use sliding window method to create samples with fixed lengths for training and testing. We could say the window slides along axis and create different samples. We could use window length and step size to control this process. And for architecture, we are inspired by deep one-class classification. In this paper, they combined one-class classification method with deep learning. Here is a figure in this paper. They used an artificial neural network to extract features from input data. And in output feature space, they try to minimize the volume of a data enclosing hypersphere. Here, the black dots represent normal samples and other means anomalies. This model first initializes the center by calculating average output value in feature space, and then try to let the normal sample close to this center. And the distances between samples and the center are used as anomaly scores. Here, for convenience, we use 2D space to represent the input and output feature space. In actual use, we could use any kind of data as input, such as images and time series data. And in the paper, they use convolutional neural network architecture for images and multi-layer perception for time series data. Different with it, we use 1D convolutional neural network for time series in this computation, which we think could better extract the features for 1D signal. Since this model is designed for unsupervised learning, it could perform well when the difference between normal samples and anomalies is obvious, which is different from the situation in this computation. So it performs poor. And then we inspired by the idea in paper deep anomaly detection with outlier exposure. They improve deep anomaly detection by training anomaly detectors against an auxiliary dataset of outliers, which enables anomaly detectors to generalize and detect unseen anomalies. And we use deep SAD as the model. It's an expanded version of the model I introduced in previous slide. It tried to at the same time minimize the volume of data enclosing hypersphere and keep abnormal samples away from the center. I provide its loss function here. It tries to minimize the distance between normal samples and center and let the anomalies away from the center. To get different outliers, we use data augmentation for time series data. Here we inspired by this paper, self-supervised representation learning for 12 lead ECG data. And in this paper, they provided several data augmentations they used for time series data. And here is a figure in this paper. Based on the ideas in this article, we designed 10 kinds of data augmentations for this computation. Here are examples of data augmentations we used. First are 3 kinds of Gaussian noise. The first is we add the Gaussian noise directly to the original signal. And the second and third are we replace the signal with the average value, either the average value in this window and either the 0. And then we add Gaussian noise directly to the signal. The fourth and fifth figure represent we resize the signal by double or half the amplitude of the signal. And the last one, we delete a sub-window of in in the signal, in the window of signal, and replaced it with a straight line by directly connecting the two sides of the sub-window. And the first one, we flip the signal around the average value of this window. And the second, we flip the signal horizontally. And dynamic time warp means it stretches and squeezes random contiguous segments of the signal along the x-axis. The last one, we replaced the value of certain point, one point, with minimum value in this video, in the window. Sorry. Here are other details we use in this computation. Result smoothing, we use it to avoid the influence of noise in result. And input processing, we use first order difference of window as new input. And we also tried to combine models by directly summing their normalized results. Different models, we could use different inputs or different convolutional neural network architecture. Here are the results we got from this computation. And if we use only single model without outlier exposure, the score is only 57.2. And we could augment the score by data augmentation or input preprocessing and result smoothing. They both augment the score. And we could see using outlier exposure with data augmentation helps a lot to improve the accuracy of anomaly detection. That's all I'd like to introduce in this video. Thank you for watching.